This is for an object undergoing motion in a circle, right? Imagine it's the Earth orbiting around the sun. So here's your sun, here's the Earth, this is not to scale, and it's traveling in more or less a circular path around the sun. Okay, now the fact that we're approximating this motion as a circle, whether it's this scenario or whether it's the ball on a string that you whirl around your head, any of those kind of scenarios, I know that my speed is always tangent to the circle, and I know that my r value, the radius of the circular path, is from one object to the other. That's r. Now, speed. The very first formula you learned in grade 11 physics was this one. Speed is equal to distance over time. And you were told many, many times through the entire grade 11 and again in grade 12 physics, and I'm going to tell you again now, you can only use this formula when the acceleration is 0. Now there's a little bit of a disclaimer there. Here we have acceleration. We just call it centripetal acceleration, but we don't have linear acceleration. So that's the fine print, okay? You can only use this formula when the linear acceleration is 0. Now, if you're moving in a circle, that means you're traveling in uniform circular motion. You have a constant speed, hence your linear acceleration is 0. Okay? The only kind of acceleration that's not 0 is centripetal. That's fine. Okay? That means I can use that expression. Now, when you're moving in a circle, the distance s you cover, it's the circumference of a circle. So assuming for one revolution, the distance you cover is 2 pi r, that's the circumference of a circle. And the time it takes for you to complete one revolution, we just gave the definition on the earlier slide. It's called period, capital T. 2 pi r over t. Now, in the equation for centripetal acceleration, I have v squared divided by r. So let's square this and see what happens. So v squared 2 pi r over t all squared. Now, if you remember your math, and I hope you know how to do this at this point because this is at this point elementary mathematics, this exponent gets applied to everything in the bracket as long as everything in the bracket is either separated through multiplication or division. So it gets applied to the 2, the pi, the r, and the t, all of them. So v squared becomes 4 pi squared r squared over t squared. We're almost there. Centripetal acceleration is v squared divided by r. So if I just take this and divide by r, it's going to be 4 pi squared r squared over t squared all over r. Okay? Now this r, I'm going to rewrite as a fraction over 1. So I have a fraction over a fraction. Now I've done this so many times. If you have a over b divided by c over d, that becomes a over b times d over c. Where you take the fraction in the denominator, you flip it, and you send it to the numerator. So what that means is I'm going to have this. So instead of dividing by r over 1, I'm multiplying by 1 over r. And guess what? I have an r squared in the numerator of the first piece, and I've got an r in the bottom of the second piece. So 1 r from each piece will cancel. And that leaves me with the correct relationship and the correct formula between centripetal acceleration and the period of the motion. Some questions will not tell you the speed that the object is traveling at. They will tell you how long it takes, and so it becomes helpful to know this expression. Now, there's actually one other expression that looks like this, but is not in your data booklet, nor do we really formally explore it in the notes. But I want to just show it to you, so in case you see it in the future, you can at least recognize it. So, using the idea of t is equal to 1 over f, right? They are reciprocals of each other. I know that frequency is also the reciprocal of period. If that's the case, then that means f squared I can also rewrite as 1 over t squared. I have 1 over t squared there, just with a constant in the top. So I can rewrite this as 4 pi squared times r f squared. So these two formulas are one and the same. The rest of the stuff on this slide is exactly this derivation. Okay? So if you copied it down here on the board already, you don't have to recopy it into the notes. Okay, and then those two formulas are at the bottom there again. Okay. So let's use this equation in an example. All right, let me erase this. Albert, the 2.50 kilogram physics cat, is being swung around by a string harness having a radius of 3.00 meters. He takes 5.00 seconds to complete one fun revolution. What are AC and FC? Okay. So I want to write down what I'm given first. I'm given the mass, 2.5 kilograms. Let's see, the radius of the circular path is 3 meters. So far I'm seeing 3 sig figs, 3 sig figs. He takes 5 seconds to complete one revolution. Remember, the time for one revolution is called the period. That's capital T. All right, what are AC and FC? So we have to figure out centripetal acceleration and centripetal force. Now, short of deriving it again, you can always look it up in your data booklets, right? In box 6.1. So make sure you have your data booklet out in front of you. Check box 6.1 for that formula. Okay, so we have A is equal to 4 pi squared r over t squared. Okay. And I'm just going to stick a little subscript C to remind myself that's centripetal acceleration. Okay, we know everything. Let's plug in our values. R is 3. T is 5. And that gets squared. Don't forget to square. We just have to plug in our values. .74 meters per second squared. I'm not going to worry about the direction here, but we know the direction is toward the center of the circular path. Okay, centripetal force, Newton's second law. You have the acceleration, multiply it by the mass, and you'll have centripetal force. Okay, so 2.5. 0, that's already an SI unit, times 4.74. Let's figure out what that is. So 2.5 times 4.74, we get 11.85. Okay, so we need this to 3 sig figs. there was a rule that I mentioned that the IB likes to use when you have to round up or round down when your last value is a 5. And the rule was, if the number that precedes the 5 is even, you round down. If it's odd, you round up. This is just a way for them to split which way to round, so it becomes easy. All right? So because we end with a 5, and this number before is even, we round down. So it doesn't round up to 11.9, it rounds down to 11.8. So 11.8 newtons. If we needed to give a direction there too, it would be towards the center of the circular path. Okay. Give me 1 second here. All right, so we've been talking a lot about the circular motion. We're going to start to introduce a slightly new topic here, still connected to circular motion and revolutions, where we're going to talk about angular velocity and angular speed. Okay, so in order to understand velocity, well, you have to understand displacement. And so therefore, in order to understand angular velocity, you have to understand angular displacement. Okay, so they go hand in hand like that. So the scenario I want you to imagine here, I mean, I've got a big black circle and I've got these 5 colored dots rotating in a circle. Now what I want you to imagine is that each of those 5 circular dots are cans of paint. Okay, each of those cans of paint has a little hole in it. And so it's going to start to trace out a circular path as it moves around the circle. Now, for a quarter of a revolution, we note how the paint actually comes on the black circle. Yeah, so we can do that for each of the colors. And what we notice is that whatever color is closest to the axis of rotation, where r is equal to 0, well, less paint comes out, right? And more paint comes out for the red, which is at the furthest distance from the center, the biggest r value. Now, there's a couple of things that are the same for all of these colors. Okay, notice that all of them cover the 360 degrees in the same amount of time. That's important. And the other important thing is we are considering them moving through the same angle. Okay, that's the angular displacement. We're considering that they're all moving through 90 degrees. Now I keep saying degrees, 360 degrees, 90 degrees. In mathematics, we've already moved from grade 11 to grade 12, going from degrees to radians. In physics so far, we have predominantly stuck to degrees. In this section, we're going to move to radians. So it shouldn't be that much bigger of a jump since you have already been doing it in math. But nonetheless, we're going to go over it. All right, so theta is the angular displacement. The displacement when you move through a certain angle. Okay, it's not linear. Now here, our angular displacement is 90 degrees for all of them. The displacement, generally speaking, displacement we always symbolize with S. Okay, so even if it's a linear displacement, if it's a curved displacement, which we call angular displacement, we'll actually give that the value S. Okay. Now, in MHF4U, advanced functions, we actually learned about something like this. When your distance covered is along a circular path, we call that arc length. So arc length, S, so I apologize if I misspoke earlier, theta is the angular displacement, S is the arc length, okay? And the arc length you can see as the color moves outward in the circle, that arc length increases, but for the same rotational velocity and the same angle. Okay, so S is the arc length. Okay. The next slide, we're going to do a review on radians. Okay, so some of you probably already remember. I hope you do. Here it is. All right, radians. 360 degrees, the rotation of an entire circle. That's 2 pi radians, okay? So 360 degrees, 2 pi radians. We actually derived where this expression came from at the beginning of MHF4U when we first introduced radians. It comes from the circumference of a unit circle. Circumference is 2 pi r, okay? Radius of a unit circle by definition is 1. So the circumference, the total distance around the circle is 2 pi. So depending on how far along the circle you were, well, that corresponds to a different angle and a different distance traveled. The distance around the full circle is 2 pi. Anyways, that's where it comes from, which means half a revolution, or 180 degrees, would be pi radians. All right, so let's try some of these examples. These will be pretty easy for you since you've already done conversion between radians and degrees. Okay. Convert 30 degrees into radians and convert 1.75 radians to degrees. Anytime you want to convert units, as I keep saying, you multiply by 1. You replace the 1 with an empty fraction and you choose the top and bottom carefully so that you can make the appropriate cancellations. So 30 degrees times 1. So I replace my 1 with empty fraction. I'm trying to get rid of degrees, so I'm going to put degrees, okay? I'm trying to get radians, so I put radians on top. Well, I need a ratio of radians to degrees that I know are equal to each other. I can use 2 pi over 360, but that's the same thing as pi over 180, right? That would be the simplest fraction. So pi, or 3.14, etc. radians, is 180 degrees. This way the units of degrees cancel, and I'm left with radians. So 30 times pi divided by 180. I'll just show you another way you can look at this. 30 pi over 180. In math, we did this quite a bit. If you divide top and bottom by 10, you get rid of the zeros. So you have 3 over 18. 3 goes into 18 6 times. So that means I get pi over 6, right? So if I divide 3 by 3, I get 1. If I divide 18 by 3, I get 6. Hence, pi over 6 radians. The other one is 1.75 radians to degrees. Again, multiply by 1. There's my empty fraction. I'm getting rid of radians, so I stick that in the bottom. I'm trying to get degrees, so I stick that on the top. Same fraction, you might just have to flip it. In this case, I have to flip it. So pi goes on the bottom. Pi radians is equivalent to 180 degrees. So radians cancel. This one you're going to have to do in your calculator, unless you can do 180 times 1.75 in your head, which, actually, now that I think about it, it's probably not that bad, but nonetheless. Then dividing that by pi, that'll be tough. 1.75 times 180 divided by pi, and we're getting, let's see here, 1.75 times 180 divided by pi. Give me 1 second. Okay, good. So we're coming up to about 100 degrees. It's 100.3 approximately. With angles, you don't worry about sig figs. So if you have an angle of 30 degrees and you take the sine of the angle, there are no sig figs involved with that. Okay, sig figs only apply to other types of measurements, not angles. Okay. Now that we understand how to go back and forth between degrees and radians, or at least now you have a better understanding of it, now let's go back to the idea of angular displacement and arc length. Okay, so this is the relationship. And again, when in MHF4U, you would have seen this. We most likely called this A. in MHF4U. Okay, so now we're going to call this S because S is displacement in other formulas that we've used as well. Okay, so here we go. Suppose the red line is located at a radius of 1.5 meters and the green line is located at 1.25 meters. Find their lengths. So I have to find the arc lengths. It's not too bad. So I'm looking for S, S for red, and S for green. Formula's right there. S is equal to R theta. Okay, so SR is equal to the radius for the red times theta for the red. Now, it tells you here the red line is located at a radius of 1.5 meters. There it is. 1.50 meters, that is 90 degrees, right? From 0 to the vertical position, that's 90. 90 degrees, but we have to put this in radians, right? You don't want to use degrees here, otherwise you're going to have a huge error. So 90 degrees is pi over 2 radians. Now I know I'm jumping the gun a little bit here, okay? So I hope you remember from MHF4U, from MCV4U, that's 90 degrees. Okay, so 1.5 times pi over 2. We have 2.356, okay, meters. Okay, let's put 3 sig figs, so that would be 2.36 meters. Okay, so that's the length of R for red. Okay, you're assuming that to be bigger than what's for green. Green is shorter even based on the picture. So let's calculate that. So SG is equal to RG theta G. So we're told in the question the green line is located at 1.25 meters. That's from the center, that's the radius. And theta is 90 degrees or pi over 2 radians. Okay, here we go. 1.25 times pi divided by 2. So 1.96 meters. Right, so this is what we would expect. So our answer makes sense. S value for red is bigger than S value for green. Okay. All right. I think in the slides, the answers are to 2 sig figs. But 3 sig figs would actually be a little better here. Okay, but it's fine. All right. So we talked about angular displacement, we talked about arc length. So the next part that would make sense is to talk about angular speed and speed. Okay, so arc length. Arc length is like a displacement, right? So it's a displacement when you move through a circular path. And displacement, just as before, so this is just an example of one of those kinematics formulas, okay? S was displacement, which is why we're using it again here. It's the distance you travel between final position and initial position. Now speed, V, is distance over time. Okay, so we can change this up a bit. So S, which is the arc length, that's R times theta. Now we can manipulate this expression a little bit. Instead of R times theta divided by T, take that theta and merge it with the T. So now you put your brackets around theta over T. Angular displacement over time. That's where we have a new value. Notice that that got replaced with a symbol that looks like a W. This W, it's curved. Don't just write a regular W. This is the Greek letter omega. In fact, this is the lowercase omega. Uppercase omega looks like this. We used it for ohms, which was the unit for resistance. So this is also omega, but this is uppercase. We're using this one. This time it's a quantity, it's not a unit, all right? So omega, that's theta over t, angular displacement per time. Okay, so that is angular speed. Okay, let me just write that in here. Now, if you put a direction with this, it becomes angular velocity. All right, So we get not only v is equal to r times omega, that's going to be the tangential speed, okay? This is the rotational speed. This is the distance from the center of the circle. You also know that omega is equal to theta over t. Just as you will remember that velocity is displacement over time, angular velocity is angular displacement over time, or angular speed is angular displacement over time. Okay. All right, now you do not have this slide in your sheets, so just follow along, and like I said, when I post these slides, you'll have the copy, plus you have the copy here. Consider the following point mass moving at a constant speed v in a circle of radius r as shown. Okay, so we have to find the period t of the point mass, the frequency f of the point mass, and the angular speed omega of the point mass. Now, based on that animation, we don't have enough information. We need some kind of timekeeping device. And so we are going to keep time like this. So looking at the animation and looking at the clock underneath, each tick represents 1 second. So just pay attention to what the period is. So let's start now. Okay, so what you should have noticed is that in the time it took for the object to go around once for the circle, the time piece, the time hand on the clock, also went around once. Okay? It passed through 12 ticks, so that's 12 seconds. So that means the period of the point mass is 12 seconds. So that was pretty easy by inspection. Part B, the frequency of the point mass. Also not too bad. Frequency is the reciprocal of period. So that's 1 divided by 12. Again, don't leave your answer like that. Figure out the decimal. Okay, so 1 divided by 12. That's 0.083 with the 3's repeated. 0.083. Now let's see for sig figs. No sig figs here because we weren't given data. We measured this, and with the clock, we're not exactly using sig figs there. So a reasonable number of sig figs would be 0.083. So that's 2 sig figs, and that's hertz. Okay. And C, the angular speed omega of the point mass. Okay. Now, angular speed, you can calculate a couple of different ways. It's either going to be theta divided by t, or you can have v divided by r. Okay, so this is how we're going to look at it. Theta divided by t. What angle did the time hand go through? Well, it went through one whole revolution. That's 2 pi radians, or 360 degrees. So omega is what we were looking for. Omega is theta over t, right? Or rather, it should be, well, yeah, we can leave it as t actually, because we don't know how much time is passing. 2 pi radians, and we know that took 12 seconds. So either you can say pi over 6 radians per second, or we can actually figure out what that is, and that comes out to be 0.52 radians per second. Again, this is rotational speed. This is not the same thing as v. So the v you see that's tangential to the circular path, that's not what we just calculated. Right now we're trying to figure out every second what angle are we passing through. V is still in meters per second. That didn't change. Okay. 2 more slides. All right, example. Find the angular speed of the second hand on a clock. If you have a clock nearby or you have a watch, pay attention to the second hand, right? So you need an analog watch for this. The angular speed of the second hand on a clock, then find the speed of the tip of the hand if it is 18 centimeters long. All right, we're looking for angular speed. I know angular speed is angular displacement divided by time. If we consider one rotation of the second hand, well, it's going to take, well, it's second hand, it'll take 60 seconds for a minute, right, for it to go through the clock once. So 60 seconds, that's one revolution. That's 2 pi radians. So pi over 30 radians per second. Let's see what that comes out to be. 2 pi divided by 60, 0.105 radians per second. Hopefully that's okay. Then, find the speed of the tip of the hand if it is 18 centimeters long. Notice in the question it says the tip of the hand. Okay, so we're dealing with the second hand here. Okay, so you have the hour, the minute, the second, the tip. The tip's important because even though the tip and, well, a point not too far from the axis of rotation, even though they're passing through the same angle in the same time, you can see that a point on the tip will move through a much bigger distance in the same time. So it has to have a much bigger speed. Okay? All right, so in order to find the speed, well, we've got V is equal to R omega. So my R, that's the distance from the center of rotation to where the object is that is rotating. That's 18 centimeters. You gotta convert that to meters. So 0.18 meters, omega, we just found. 0.105. So we multiply these out. So 0.18 times 0.105, and we get 0.0189. So that's 3 sig figs, actually, so I think we're good there. Meters per second. Remember, if you're using any of these formulas, as long as you plug in SI units, you will get SI units out. So what I was explaining there, that the tip moves faster than a point closer to the middle, I mean, that's what this last point is communicating. The last slide we're going to do now. An example. All right, a car rounds a 90-degree turn in 6 seconds. What is its angular speed during the turn? All right, so we're looking for omega. We know it's a 90-degree turn. And we know it takes that turn in 6 seconds. We have to convert the angle to radians. Okay, so 90 degrees, that's pi over 2 radians. Okay, so now we're looking for omega. Omega is theta over t. So that's pi over 2 divided by 6. So whatever that turns out to be, that's pi over 12. So we get 0.26, yeah, 6.0 seconds is 2 sig figs. Don't use the angle. The angle only has 1 sig fig, but we do not use that in our determination of sig figs for our final answer. So 2 sig figs in your final answer, and we are calculating omega, so that's radians per second. It's only angular speed, so no direction required. Later on, you will learn and you will see how to calculate, well, not how to calculate, but how to determine the direction of this angular velocity, okay? So that is the end of 6.1 part 1 of 3. Next video will be 6.1 part 2 of 3. Okay, so stay tuned.